In this video, I'd like to talk about carbocation rearrangements. And this is going to be something relevant for SN1 type substitution mechanisms. But in fact, it's actually relevant for anything which goes through a carbocation. Anytime you generate a carbocation, it's entirely possible that you get rearrangements, most typically 1-2 shifts. And the 1-2 shifts that I'm referring to are generally either alkyl or hydride. And this is usually on undergraduate tests at the second year organic level. So it's something that you basically need to know. And let's just break this down in terms of the three types of things that you'll typically see on an exam. And so the first example I'll give you will be something like this. We won't bother ourselves with the stereochemistry. So let's say we have this. And if this goes by an SN1 reaction, and of course we know the leaving group leaves, and what we get is a secondary carbocation, right? Secondary carbocation. Well, there's a potential tertiary position right here. So if the carbocation wants to stabilize itself, and it certainly does, then you can get a 1-2 shift. Now, interestingly, if you do the 1-2 shift with the methyl group, let's say this methyl group shifts. In other words, this entire bond and its 2 electrons just moves over to the neighboring carbon. The methyl group takes its bonding electrons with it and simply hops over to the other carbon atom, to the neighboring carbon atom at C3. Well, what we get is basically the same thing we had before. We still have a secondary carbocation and a potential tertiary position, because the methyl group moving over has just moved where the tertiary position is and where the cation is, but didn't really fundamentally change anything. Now, the other thing that can shift is the hydride. In other words, this hydrogen atom can pick up and take both of its bonding electrons with it and simply shift over like this. And in fact, if it does that, then we have finally gone from a secondary carbocation to a tertiary carbocation. This position is still secondary, and the carbocation is now perched on a tertiary carbon. So the carbocation has enabled itself to sit on a tertiary carbon where it used to sit on a secondary carbon. And so there's a great deal of stabilization that comes from this. And of course, when the nucleophile attacks, this is the product that you get, right? And of course, the product that you might have expected, the product that you might have expected was this, right? If you just consider a typical SN1 reaction, this is the product you would expect. You would expect the bromine to leave behind a carbocation, right, at C3. I'll actually show the carbocation once more, this one right here. And you would expect that this would be the product. But in fact, this is the product after you get the rearrangement. And so carbocation rearrangements are always something that you need to be on the lookout for. So let's give another example. Something that is usually on undergraduate level exams. And that would be something like this. Anything with this type of system. You can have anything on this side or on this side. And of course, SN1 means we get a carbocation, secondary. And if you look closely, you'll see that this is a quaternary carbon center. But if one of those alkyl groups moves, then there is the potential to have a tertiary position for a carbocation. And that's precisely what happens. One of these CH3s can just do a 1-2 shift. Position 1, position 2, you can say. It just does a 1-2 shift like this. And what you get is this. You now have a tertiary carbocation. And when the nucleophile finally comes in to trap the carbocation, nucleophile could be anything. It could be methanol. It could be water. What you get, of course, is this. That's what you get. And of course, what you expected would have been this, right? This is what you might have expected. So this is another case where you can generate a carbocation and either a hydride or an alkyl group that's neighboring to the carbocation can shift. Now there's a very interesting other thing that can happen. And this is something that usually stumps undergraduates. Okay, so let's think about this. We have a ring structure. And this time we have, by the way, I'm drawing secondary alkyl bromides. You could draw this with primary bromides and generate a primary carbocation, which would obviously be ripe for alkyl shifts or hydride shifts. But typically you don't see the formation of primary carbocations. So I'm not really drawing that. These are secondary carbocations. So okay, SN1. What do we get? We get this, a secondary carbocation. Now you may say, well, here we have our methyl group that can shift, right? And so we could get this. And our nucleophile could come in, right? Trap it. And the product that we would get would be this. And that's correct. Isn't really any problem with that. However, there is something else that can happen in this case, which is more interesting. And that is that the endocyclic bond can shift. So this bond here that's making up the ring can do the same shift like so. And what you get is you actually get a ring expanded product. So now what we have is a methyl group, and a tertiary carbocation like this. And when the nucleophile attacks this carbocation, this is what you get. So the point is that whenever you generate a carbocation, you can get a rearrangement. A hydride can shift, an alkyl can shift, and there's very often a couple of groups that might be able to shift. And very, very often you can really start to get very complex mixtures as soon as groups start moving back and forth. And one of these is generally the type of rearrangement that you would expect to see on an undergraduate exam.